Hello dear students. Today's topic is bonding in coordination compounds, valence bond theory. Coordination compounds don't follow Lewis octet rule. That means they don't bond to complete 8 electrons in their outermost shell. So why do then they bond? That is the question. Werner first tried to explain this coordinate bonding as secondary valency. He called this coordinate bonding, as secondary valency of central metal atom. But he could not explain with help of this theory that why there are directive, magnetic and optical properties of the coordination compounds. Directive properties means they have geometrical shape, particular geometrical shape in space. They have magnetic properties, means they can be either diamagnetic, paramagnetic or ferromagnetic, and optical properties means they have colors, deeper or lighter, but they have some colors, or they might not be having any color. Therefore, there are 4 or 5 more theories which have been put forth to explain the bonding in coordination compounds. Today we are going to discuss only valence bond theory. Valence bond theory is a very simple kind of theory. There are not much complications in it. So ligands donate lone pairs of electrons to metal atom or ions. If they are donating lone pairs means 2 electrons at one go, okay, they are donated. The metal atom or ion which is accepting those electrons should have some empty orbitals on it to receive them. Now S and P block elements, they cannot provide empty orbitals because they do not have simply d orbitals, empty d orbitals of suitable energy. Therefore, only D block elements, most of the coordination compounds are formed by D block elements and some by F block elements as well. These D block elements have empty d orbitals. D orbitals, they combine with S and P orbitals of comparable energy. Comparable energies means they have almost similar energies. They should belong to either the same shell or just the next shell, like that, to give hybridized orbitals that are spaced in definite geometrical shape, which explains directive nature of coordinate bonds. Ligands can donate lone pairs of electrons in these empty hybridized orbitals and simultaneously overlap with them. Now let's study these hybridizations which are in syllabus one by one. First one is sp3 hybridization. Now in this S you can see that there is 1 at the top, superscript, and 3 is the superscript for P. So 1 and 3, there are 4 orbitals that are going to combine, 1 s orbital and 3 p orbitals are going to combine to give 4 hybridized orbitals. Now these 4 hybridized orbitals which is called sp3 hybridization, they have tetrahedral shape in space. One of the examples we can take is a tetrachloridonickelate 2 ion, in which nickel has +2 oxidation state and atomic number of nickel is 28. So its electronic configuration would be argon 3d8 4s2. Now when it forms a bivalent ion configuration. Now in this 3d8 configuration, this is the orbital picture. You can see 4s and 4p are empty and they are going to combine to give sp3 hybridization, while 3d orbitals, 3d electrons stay as such. Now you can see that there are 2 unpaired electrons. When a complex is being formed, 2 unpaired electrons stay there. Okay. Now because of these 2 unpaired electrons, this particular ion, complex ion, is paramagnetic in nature, and we are going to calculate this mu, that is magnetic moment, in the next slide. Before that, let's see dsp2 hybridization, because we are going to compare both of them, because nickel forms both kind. Nickel undergoes both kind of hybridization. So dsp2 hybridization, as the name suggests, you can see there is one d orbital combining with one s and two p orbitals to give four again dsp2 orbitals with same energy, and they are having a square planar shape. Now example is tetracyanidoniclate 2 ion. Here again same electronic configuration of nickel, nickel ion, same configuration. Here you can see that 3d orbitals is having 8 electron, 4s is empty, 4p is empty. But what is the difference between this dsp2 and sp3 that you just saw is one electron is moving from its orbital to the orbital which is having one electron already. So this electron, the electron gets paired, okay, and therefore this d orbital is empty now, and it combines with this s and these two p orbitals. Now this p is again is single, and these four stay together. They are having the same energy, okay, dsp2 orbitals. Now cyanide ligands give four lone pairs of electrons to these four dsp2 orbitals. Now you can see here I have written here, I forgot to write chlorine. Now this is a shape of tetrahedral uh, tetra chloridonucleate ion, and this is tetracyanidoniclate 2 ion, and this one is also having sp3 hybridization where nickel is in zero oxidation state. This is tetracarbonyl nickel, okay, there is no ion or there is no charge on it. Next is comparison between the magnetic moment of the two. Now in sp3 hybridization, as we discussed, there are two electrons which are unpaired. Therefore you can calculate it's a spin only magnetic moment with this formula: mu spin n plus 2 square root. Now it comes equal to 2.83. Just look at the calculation. In dsp2 hybridization, on the other hand, there was no unpaired electron. Therefore mu is 0. It won't show any magnetic properties. Now we are going to compare d2sp3 and sp3d2 hybridization. Both of them, you can check, there are 6 hybrid orbitals in both of them, 2d plus 1s plus 3p orbitals. So total 6 orbitals are there, and they have octahedral shape. Here, what is the difference between the two? In this one, where d2sp3, d orbitals are taken from penultimate shell, okay, while in this one the d orbitals are taken from, they are combining with sp3 orbitals, they are taken from the same shell, okay. That is a difference. We are going to just see with an example with for each. Now these types of hybridization occur when two d orbitals combine with one s and three p orbitals, okay. Now in the next slide we can see the examples. Here this is hexafluoridocobaltate 3 ion. Cobalt atomic number is 27, so it can be written as argon 3d7 4s2, and cobalt 3 ion oxidation state is 3. So the resultant electronic configuration can be given as argon 3d6. Here orbital diagram is given. Now 3d6 and 4s is empty, 4p is empty, and 4d is empty, okay. Now in this case, sp3d2 case, as I told you that in sp3d2 the d orbitals come from the outermost shell, the same shell to which s and p orbitals belong, okay. You can see that they have combined here. So out of these 3d is untouched, okay. Now you saw that there were 4 unpaired electrons, and therefore magnetic moment would be, as the calculation n plus 2 again and square root gives you 4.89. This is high magnetic moment, and therefore such kind of complexes, sp3d2 hybridization complexes, are called high spin complexes. Next is D2sp3 hybridization. Now examples are hexaamine cobalt 3 ion and hexacyanido cobaltate 3 ion. Now in the both the cases, cobalt is having 3 plus, again the same oxidation state. Okay, so we just go through it, and you can see now d orbitals are from the, as I told you, penultimate shell, right? Now two, and there is no empty d orbital, so what's going to happen? These two electrons from 3d are going to shift to the other two orbitals, 3d orbitals. Okay, and they are going to pair up. Now there are two empty d orbitals, so they are going to combine with s of the next shell, and similarly for p of the next shell, like this. So there are 6 orbitals. This kind of hybridization is D2sp3. They are called inner orbital complexes. Earlier was outer orbital complexes. There is no unpaired electron. Therefore, they are called low spin complexes. Mu is 0 basically. Now I have given shapes here. At the end, so you saw that VBT could explain the direction. VBT could give magnetic moment as well. What VBT could not give? VBT could not explain the color of the complexes. Okay, and now VBT could not explain why, as you saw, cobalt is giving 2 types, nickel is giving 2 types, right? Inner orbital complexes and outer orbital complexes. So why it's happening that with some ligands, they both are giving, nickel and cobalt are giving inner orbital, while with some other ligands, they are giving outer orbital complexes. And therefore, VBT is considered as oversimplified approach towards explanation of complex compounds. Now, I hope that this was helpful, today's topic, and I would be coming with next topic very soon. Till then, you take care and bye-bye. Whereas 2 electrons, they are given, and the resulting ion has 3d8